So, going back to the proof of backward direction. Suppose B contains the circle is invariant under the rotation. And we want to show that the measure of B is either 0 or 1. Now the idea of the proof is very interesting. Instead of using just set theoretical methods, we're going to use functions. First, try to recall what function only has values 0 or 1 and measurable. You should be able to come up with the answer immediately. So that function is an indicator function or characteristic function. So the idea of the proof is that you consider the characteristic function. If you can show that the measure of B is close to the characteristic function in some way, then it has to be either 0 or 1. And how to measure the difference between this measure, which is scalar, and this function? We have to use some norm on functions. The trick is that you are going to consider the difference between this measure and this function under the L1 norm. And you want to show that this guy is as small as you want. That's the idea. And the tricky part will be to use the triangular inequality and some approximations to bound this. So for any epsilon greater than 0, the really tricky part is that you're going to insert in between some other stuff, some other functions, and use the triangular inequality to split this norm. The trick is the following. For this epsilon, you choose a function, a continuous function, f on the circle with the L1 norm between f and chi sub b is bounded by epsilon. This choice is guaranteed by some theorems in real analysis. Some of you remember it, some of you don't. So let me remind you. This follows from the Forlan's real analysis, second edition, page 217, theorem 7.8 and proposition 7.9. The theorem 7.8 in Forlan's book basically tells you that this Lebesgue measure on this circle is a Radon measure. And the proposition 7.9 tells you that if you have a compact space, then the continuous functions on this compact space is dense in L1 norm. Namely, you can approximate any integrable function by a continuous function on this circle. And this is the one part of the splits of this L1 norm by triangular inequality. There are two more parts. So where are we going to use this fact? Where are we going to use that the multiples of irrational numbers mod 1 is dense on the circle? This fact will be used in approximation. So the fact above will be used to bound the following: that the L1 norm of f and its integration over the circle, this norm is supposed to be very small. This is a very tricky part. Let's just leave it alone for the moment. Remember, we want to split this into 3 parts using the triangular inequality. So you get 2 parts, and you know the rest. So you're going to split this into, the first part is f minus chi sub b, L1 norm, and the second part is this guy, the difference between f and the average of f in L1 norm. And third part is the average and mu of b difference. Actually, this average and this measure are just both scalars, which means this L1 norm is nothing but the absolute value, because our integration is taken over the circle, and that circle has full measure 1. So this part will be simply equal to the absolute value of the difference between the measure and the function. So the L1 norm here is simply the difference between this average and the measure and their absolute value. And this absolute value, if we change this measure to the integration of the characteristic function over the circle, so this will just be the difference between 2 integrals, and this is bounded by the integral of the absolute value of those 2 functions over the circle. And this is precisely equal to the first guy. Namely, since by our construction the first guy is bounded by epsilon, and the third guy is the same as the first guy, and the third guy is bounded by something that is same as the first guy. So the third guy is also bounded by epsilon. So now we have 2 epsilons. It remains to bound this guy. If we can show that this guy is also epsilonly small, then we are done. But this will be somewhat tricky, and we need to use the fact above. The middle term which is the L1 norm of the difference between f and its average over t, can be written explicitly as, so first there's a big integral, and here's the absolute value of f minus its average. This should be dx, and the variable here should be x. And this big integral is still over t. Now we do something with this integral. What we are going to do is that we're going to change this t to x plus t. So let me write this down again. By change of variable, we change the integrand in this small integral from f of t to f of x plus t, still integrated over the circle. And because the measure of this whole circle is 1, and this is a constant, we can always change the constant to an integral. So what we're going to do is that we're going to integrate this constant over this circle. And now you know the trick. This guy will be equal to the absolute value of the integral over the circle with integrand fx minus f of x plus t dt. And the outside integral is integrated over x. Oh, I forgot to say, so some of you know why this is true and some of you don't. So the reason that we can change t to x plus t without affecting this integral is because this f is defined on this circle, and this integrand is always considered as something mod 1. You can always think of f as a periodic function on the real line with period 1. And when you restrict it to the circle, you can do a change of variable formula to show that this integral is same as this one, just by the elementary calculus. And this last term is bounded by this double integral of the absolute value of the difference of those two functions, dt dx. However, by Fubini's theorem, you can flip those two integrals. So this, by Fubini's theorem, will be equal to the integral where we first integrate this function with respect to x and then by t. And now we look at this part. This part can be associated to the rotation. Do you see how? I'll let you think about it. The observation is that this guy is same as f composed with RT apply to x. Namely, you first add t to x mod 1, and then you apply f to x plus t. Okay, now this part will be equal to the L1 norm of f minus f composed with RT. Now, if you can somehow show that this guy is very small, is absolutely small, then this whole integral will be small, because this measure of the whole thing, the measure of the circle, is just 1. So if you have a bound for the inner integral, you have the bound for the whole thing. So why is this guy absolutely small? Now it is time for us to use this fact that we proved at the beginning. Because z times alpha plus z mod z is dense in t equals r mod z. Because of this, for this given t, and any delta greater than 0, there exists n that only depends on t and delta, such that the absolute value of n alpha minus t mod 1 is very small, smaller than delta. And you can rewrite this in terms of the rotation function. Using the language of rotation, this is the same as that the absolute value of this rotation applied to any point x in t minus the rotation by t applied to x is bounded by delta. Now, since f is continuous on t and t is compact, f is uniformly continuous. That means if you can choose this delta to be small enough, then you will have that f composed with r alpha raised to the power n applied to x minus f composed with r sub t applied to x, taking absolute value, is bounded by epsilon. And this further tells you that the L1 norm of those two functions can be bounded also by epsilon. Okay, now we are very close to our goal of bounding this L1 norm. This is very close to this. What we do here is that we consider the L1 norm of the difference of those two guys and bound it above using the triangular inequality by those two guys. First, the L1 norm of the difference of those two things, and second, the L1 norm of the difference of f composed with this n rotation of alpha and f. The first guy we already know is bounded about by epsilon. And the second guy, what is the second guy? The second guy can be further split into two parts. One is this function minus chi sub b, and second is chi sub b minus this function f, both taking L1 norm. Actually, you may observe that they're actually the same. That is because b is chosen at the beginning to be invariant under R alpha. So this chi sub b is same as chi sub b composed with R alpha. And it doesn't matter if we compose R sub alpha n many times. And because this integration is irrelevant of the rotation of the integrand over the circle, so you can drop those R alpha n at the same time, and this thing will be same as this thing. So the last two parts are both bounded by epsilon by our choice of these continuous functions on the circle, and that is guaranteed by some theorems in Forlan's book. So in the end, this is going to be bounded by 3 epsilon. So we successfully bound this guy by splitting this into 3 parts with triangular inequality, with 2 parts bounded by epsilon, and the part in the middle is bounded by 3 epsilon. And this part is the most technical part. We will apply the triangular inequality again to this part. So in the end, the whole thing is bounded by 5 epsilon. Anyway, this is a very small number. Let epsilon goes 0, you get chi sub b and mu of b are actually equal almost everywhere. What does that mean? That means that chi sub b is essentially a constant modulo a set of measure 0. When chi sub b is a constant, it will be either constantly 1 or constantly 0. So it follows that mu of b should be either 1 or 0. And that finishes our proof. So let epsilon go to 0, we'll have chi sub b is constant, and that gives us that mu of b is 0 or 1. That finishes the proof. And actually, I should move this thing to the end of the proof, the true end of the proof. Okay, so we are done.